So this is what we covered last week, and so hopefully we can continue with our lesson today. Okay, all right. So last time, where we stopped was at the first order forward difference equations. Okay, so the equation 4.0, excuse me. The equation 4.4 here refers to the John Anderson textbook. Okay, so if you're confused about the numbering, about the equations, kindly refer to the John Anderson textbook. Okay, so John Anderson. So all right. So just to recap, so for the first order forward difference, so the du dx basically refers to the slope of the equations that we're looking at. Okay, and the name itself, the first order difference. Okay, the first order refers to this part over here. Okay, okay. So the delta x here, because the highest order is first, so that's why it's called the first order. Okay, if we got delta x square, for example, then it is a second order equation. And then forward, because we are trying to estimate the value of x2 over here. Okay, you can see there, the x2 here in our element. So we are using basically, we are estimating a value on the right from the origin, on the right side of the origin here. So this is the origin that we have in the middle. So forward difference is basically we are moving to the right side. Okay, we are trying to estimate the value on our right side by using this approximation. Okay, so now let's try to write the Taylor series expansion for ui minus j. Okay, so ui minus j, if you refer to the figure over here, is the one on the left side here. Okay, so we'll try to write down the Taylor series expansion for the following variables I minus 1 j. So remember, this is our origin in the middle here, P. Okay, so to do that, again, we can just refer to equation 4.1 about the Taylor series expansion. Okay, and basically, this is 4.1 is for the forward difference. Basically, we are trying to estimate ui plus 1. Now, instead of ui plus 1, we just need to change that into ui minus 1 j. And let's see what we get. Okay. All right. So to do that, if you write down ui minus 1 j, this is the equations that you're going to get. Okay. So the first one is just uij. Okay. Uij is just the origin. And then remember, because you're trying to approximate the variables or the value on the next node on the left. Okay. So your delta x now is delta x negative. Okay. Delta x is positive to the right, but now you're moving to the left. So your delta x is now negative. Okay. So I highlighted over here, negative. And then the rest of the terms are just the same. Okay. You're going to have a second second order term over here. Okay, so you have negative x squared divided by 2 and followed by the consequent continuing term over here. Okay, remember there is a more terms on the right side. Okay, which you can continue, so it can be to the power of 4 here. Okay, plus, okay, remember negative plus x divided by, this should be 4 exclamation mark to the power of 4, and it can continue to the right side. Okay, because I think last time one of the students asked basically how do we get the terms on the right side in terms of the numbering 6, 2, and so on and so forth. Okay, so it's all because of the notation here. Okay, so when you do that, okay, when you expand it, okay, in John Anderson textbook, if you look at equation 4.5, okay, remember to take care of the sign convention. Okay, because we have negative delta x. Okay, so if you look over here, because this is negative, okay, on the first order term, because that's negative, you're going to have negative up front here because you move the negative sign from the right side to the left. Okay, basically you just move to, oh, just 1 second. Okay, so you just move, okay, the negative over here. So you have the first negative. And next one, because you have negative delta x squared, so you will have a positive sign here. Okay, and then next one, you have negative x to the power of cube to the power of 3. So because to the power of cube, then you have a negative sign over here, and so on and so forth. Okay, so remember to take care of the sign. And next, when you solve for du dx, okay, for ij, you are going to obtain equation 4.6, which is the first order backward difference. Okay, so previous one, we have the first order forward difference, okay, FD, forward difference, and now you have first order backward difference, so BD and FD. Okay, so if you can see, if you can look at the screen in terms of the equation, so du dx is equals to uij here, which is the origin, minus ui minus 1j, which is the left. Okay, so divided by delta x and plus the higher order terms on the right side. Okay, again, if you look at the sign convention, because this is the highest order is the first order, so it's called first order, and backward difference because now we are looking at the variables on the left side, so that's why we call it backwards difference. Okay, all right. Okay, so however, in most of the applications in CFD, dealing with the first order accuracy is just not enough. Okay, because we are dealing with we want something that is more accurate. Okay, so to do that, we can try to obtain the second order accuracy. Okay, to do that, basically what you need to do is you have equation 4.5, okay, which is this is the backward difference, and you minus equation 4.1, which is the forward difference. So if you can see over here, I minus 1j, and this one over here, I plus 1j. Okay, so if you do that, okay, subtraction, you are going to get, okay, basically the right term minus the left term. Okay, you are going to get equation 4.7. Okay, remember this is from forward, basically forward difference minus backward difference. Okay, so this is backward difference, this is forward difference. Okay. Okay, so when you rearrange everything, okay, you want to get in terms of du dx, you will get the following equations 4.8 as ui plus 1j minus ui minus, sorry, the first one is plus 1j, the second one is I minus 1j, the first one plus, second minus, and divided by 2 delta x. Okay, so I'm going to delete this. Okay, and plus, now you have delta x squared. Okay, so because we have a higher order terms, okay, now we call it the second order because now we have a second order term, central difference. Okay, so the questions that can be asked, okay, why we call it central difference. Okay, I think second order is quite self-explanatory because of the second order term that we have on the right side. But the question is why it is called the central difference. Okay, so if you look again at the element grid, this is the origin, and if you look at the equations 4.8, ui plus 1j, ui plus 1j is here. Let's say this is A. Let's write this A. ui minus 1j is on the left side, so this is B. And divided by delta 2ax. So again, if you look over here, this is delta, this is delta as well. So you have 2 delta ax, and basically you have the right side A minus B divided by 2 delta x. So that's why you call it the central difference. Okay, central difference, because now you are getting the value in the middle of the grid. Okay, the origin value. Okay, so again on the right side, the highest order term is the second order, and this on the right side, okay, the higher order term refers to the truncation error. Okay, so we have covered basically the forward difference. Okay, basically we use the right side of the element and minus the origin. The backwards difference, basically we have the left side minus the origin, and now we have the central difference, which is basically using the right and left element to calculate the origin. Okay, so forward difference and backward difference, these are the first order term, and for central difference, this is the second order term. Okay, so the other question is, we kind of covered the first, the forward difference, backward difference, central difference. But the question is it all? Is that all that we need for CFD or for the FDM methods? Okay. So if you look over here, if we are dealing with the inviscid flow, meaning that we do ignore the viscosity term, okay, which is the Euler equations, then what we look at FD, BD, and CD should be sufficient. Okay. Why? The question is because the highest order derivatives which appear in the Euler equations are the first partial derivative. Okay, because if we ignore inviscid flow, we get the Euler equations, and in Euler equations, we are dealing with the first order or the first partial derivative. Okay, so the finite difference for the first derivative, which is given in 4.6, 4.4, and 4.8, are all that we need for numerical simulation for the inviscid flow, okay, where we ignore the viscosity. Okay, now if you look for the next one, but when we are dealing with viscous, or if we take into account the viscous term, then we are dealing with the Navier-Stokes equations, the full Navier-Stokes equations. And for the Navier-Stokes equations, the highest order derivatives in the given equations are the second partial derivative. Okay, so you can see from the notes in John Anderson textbook. Okay, the highest order derivative which appear in the Navier-Stokes equation are the second partial derivative. So meaning that we just cannot stop at the first order derivative. We need to add some more derivative to get a more accurate result or to solve the problem related to the viscous term. Okay. All right. So how can we do that? Okay. Again, we can start from equation 4.1 and 4.5. So just now we subtract them, but now to get the second order derivative, we add them together. Okay, we add equation 4.1. This is forward difference, and equation 4.5, which is the backward difference. When you add them, okay, let's see, can you just spend 2-3 minutes whether you can solve for the second order terms here, d square u dx square. So let's take 2 or 3 minutes just to see whether you manage to get or to highlight this term, d square u and dx square. Okay, let's take 2 or 3 minutes. Okay, so are we done with FDM? No, the short answer to that is no, because what we have just discussed is the very basic of the finite difference method. Basically, just the derivation of finite difference. What is finite difference? Okay, the very, very fundamental of it. From there, basically, we can have a more advanced discussion, which I'm going to show briefly what does it mean on the details of how we can use FDM with or to basically use FDM to investigate the diffusion, or the phenomena in CFD, in fluid flow. Okay, so we are not quite done yet. So let's move to the second one, with FDM. Okay. All right. Okay. So basically, this is a recap of FDM, and I have one very simple example to show basically what we just learned. What is basically forward difference, backward difference, and also the central difference, and how it can be used basically in terms of algebraic terms. Okay. To recap, yes, we covered about the basic concept, which is basically the finite difference method is basically an approximation method. We have a set of function, and the FDM is used to approximate the function. So instead of giving the exact value, we now use Taylor series expansion to approximate the given function. Okay. So of course, the first step that we have to do is we have to define our elemental grid or numerical grid. So we look at the grid before, and the ij definition over here. So basically, this is in x component direction, this is in y component direction, I in x, j in y. Okay, so that's the first step. So to approximate the derivative, remember for du dx of ij, this is basically a slope, okay, slope that we want to estimate of. So, so using Taylor series, we can try to estimate the given function, okay. So from this grid, basically, what we are trying to do is we define the nodes I and j. This is in 2D, and unknown value of the field variable, okay, which depends on the neighboring nodes, okay, provide one algebraic equation. So I think this is the end target you have to understand. We want to have an algebraic equations. Remember, for discretization, the purpose of discretization is to change the form of a function into an algebraic equations that is uh, easier to be understood by the software or by the user. Okay, and these algebraic equations basically it is an approximation of the real function. Okay, so that's the key here. You need to understand. And if you look carefully here on the definition, we are trying to estimate the value of the neighbor by using value from the neighboring neighbor. So basically, if you want to estimate this value, we are trying to get that particular value by using the value from its neighbor. So in this case, here, okay, for x component at least. Okay, for y component, if we want to get this value, okay, for y, then we can get, or we can use the neighboring value to get this value. Okay, so that's the gist of it. Okay, for the FDM finite difference method. Okay, all right. Okay, so just now we just look in terms of elemental grid, and we look at the equations of how we come up with the equations for forward difference, backward difference, and central difference. Okay, so if you can see over here, okay, so now we understand that the du dx from the Taylor series expansion, that basically refers to the slope of a function or a plot. Okay, and the du dx, okay, can be approximated as the limit of delta x approaches 0. It can be defined as the following function. And if you look at the function given here, okay, this is quite similar to what we looked before, which is in terms of finite difference, FD. Okay, all right. So for the geometrical interpretation, so now we understand that the slope of the tangent to the curve ux is the du dx, and we are trying to approximate that particular point or that particular function. Okay. Okay. Now instead of looking at the grid, okay, elemental grid just now, just 1 second. Just now we look at the elemental grid like this, something like this. But now let's look in terms of the plot. Okay, similar concept but different application. So now let's say we have I over here in the middle, xi, and then we have xi plus 1 on the right side, and similarly I minus 1 on the left side. Okay, and to approximate this particular point on the plot, okay, if we have a straight line like this, okay, and we understand the slope is just du dx, okay, that's how you get the slope, the value of the slope. Okay, so that's the exact value. The du dx is the exact value. Okay, apart from using du dx, now we are trying to use FDM to approximate. That's what we have been discussing about the basics before. We want to approximate this particular value on the slope, okay, on this point. Okay, so from previous discussion, okay, we look at how we define the backward difference. So backward difference, basically, we have xi minus 1 and also xi. Okay, so we use that. For forward difference, we use I plus 1 and I. Okay, so we covered this as well. Now, we have for the central difference, we use I minus 1 and also I plus 1, okay, on both sides. So I think that's the basic that we need to understand first. Okay, now, so what we are trying to do basically from the FDM is, again, I repeat or I emphasize, is to estimate the function, okay, on that particular point. Okay, so some notes over here, if you can see, some approximations are better than others. Okay, we are going to look into details in a few moments. Okay, so but this is what we want to highlight. And the quality of the approximation improves as delta x is made smaller. Again, we're going to focus on this. So I think these 2 points are very, very critical, and you need to keep in mind, okay, before we go further, okay, for FDM. Okay, just give me 1 second, okay? Okay, so so these 2 points are very, very important, okay, which we are going to highlight in a few moments, okay? Right. Now, so let's have a look, okay, this very simple plot that we have at the bottom of the page here, okay? So, okay, I think let's move on here. Okay, so we have these 3 plots. Let's look one by one, okay? For the exact slope definition, du dx, okay, is given here. But if you can see here, I'm going to use another color. Let's use one. Okay. This line here, the dotted line, refers to the forward difference method, which basically we are using this value xi plus 1 and also xi. So these two, the approximate line, so the forward difference, this is FD line, which basically for approximation. Okay, basically uses 2 values to approximate the same function as the du dx, okay, to approximate. So it uses xi here, and also this one, xi plus 1. So that's why it is called the forward difference, because we have xi plus 1 and xy term. Okay, similarly, on the right one here, this is the exact value, again, touching the tangent of the plot or the graph. So for finite difference approximation, for the backward difference, again, backwards, basically we are using, let's use another color. The backward difference, we are using the xi and also the xi minus 1. Okay, these two lines. So if I can highlight again, so that's the approximation lines that we have. And for the last one, which is the central difference, if you can see here, this is the exact plot, and the central lines basically from these two, x minus 1 and x plus 1. Okay. So please take a few moments to understand what those lines refer to. Okay. So forward difference, we have this line which touches the 2 points on the plot. Backward difference touches 2 points, okay, xi and x minus 1, and central difference, it touches these 2 points, okay, x minus 1 and x plus I plus 1. Okay, so to go back to the question just now, which of the approximation give the highest accuracy? Okay, just by looking at the plots here. Remember, our target is here. This is the exact value that we want, du dx. This is du dx. And again, this is du dx. Okay, just by looking at the plot, which of the approximation you think will give the best value? If we look one by one, okay, first one, if we look at the forward difference, because it is an approximation, if you take these two value, let's say value 1 and this is value 2, you take this value and you find the value in the middle, because basically we have xi plus 1 minus xi divided by 2, okay, delta. So this is delta x, okay, similar to this. Okay, by using forward difference, you will get a value that is somehow in the middle here, okay, the dotted, the pink dotted line here, okay, which is to the right side of the exact value. Remember, this is the exact value. Similarly, if I use again same example, okay, when we are using this is exact value and this is the second point, by using the backward difference, when you find or when you calculate the value here, the approximation, this is delta x, your approximation will give a value slightly to the left of xi, meaning that your value is close to 1. This is our exact value, but it is to the left. Okay, and the last one for central difference, okay, this is 0.1, 0.2. This is the exact point that we want in the middle. Okay, and when you calculate these two, this is again delta x. Okay, when you find the medium, okay, because you have xi plus 1 minus xi minus 1 divided by 2, delta x, you will get a value that is here, which is the closest to the approximated or the exact value. Okay, so as the question to which of the approximation method give the highest accuracy, so you can see from the simple example just now, by using central difference method will or should provide the closest value, the closest approximated value to the function that we want, or the du dx value. Okay, all right. So, okay, again, okay, so this basically the equations that we looked before, basically how the definition of the backward difference, forward difference, and central difference. So if you look over here, ui and ui minus 1 for backward difference, what you're going to get is basically this. So this is for backward difference. Remember, this is the exact value. And let's change color. For forward difference, you are going to get this is forward difference. And finally, for central difference, you can see over here, you are going to get the closest value to the exact value. So this is central difference. Okay, so hopefully you can understand or appreciate the approximation method. We have several methods, but each method has the pros and cons. So based on the simple analogy or examples that we discussed just now, central difference give the highest accuracy compared to forward difference and also the backward difference. Okay, all right. So, okay, I've got a few more, but I think we are going to stop here for today. And hopefully for next week, we'll continue from here. And then we are going to look at a few example problems on the applications of the finite difference method. Okay, so before we end, any questions from students regarding what we just covered in this lecture?
Doctor,
Yes.
is it always the central difference would be best approximation?
Come again, Ashiko?
Uh, the central difference would be always the best, or is it varies case to case basis?
All right, thank you, Ashiko. The best is subjective, but based on the simple analogy or examples that we look at before, it will give the closest approximated value. So let me give you an example. Let's say, let's say this is our value. Let's say this is 1. Okay, let's say the exact value is 1. Exact value. Okay, this is 1. And if we use a forward difference based on the simple example that we looked before from the graph, our value will be to the right, meaning that we'll get maybe 1.001, something like that. Okay, and if we use this is for forward difference, backward difference might be negative, it's not negative, 0.998, for example. Okay, so by comparing to this, if we use a central difference, we are expecting a value. Okay, maybe the value that I'm using is not, it's not too good. I'm going to erase this. Let's use another value. So let's say maybe 1. Let's say 1.1. This is forward difference, and backward difference maybe 0.9, for example. So maybe by using central difference, we should be getting closer to 1. So maybe, for example, 0.99 or maybe 1.01, for example. Okay, so not to say the best, Ashiko. I think that's very, very subjective. I think the best in CFD is very, very subjective. So we don't usually use that words. But the closest, because it's all about accuracy in CFD. So I would say central difference would give the closest value to the exact function that we want. Okay, hopefully that answers your question. All right, anyone else? Anyone? All right. Okay, so if there is nothing, thank you everyone. I'll see you next week. Okay, assalamualaikum. Very good evening.
Thank you, Doctor.